Hello, everyone. I'm Channing. Today, I will present our work, M3. Network operators often need to predict the network performance. In data center networks, we care about the network tail latency and the utilization in different situations. For example, how would the network tail latency be affected if workloads evolve? What if we use a new congestion control protocol and its new parameters? A common way to predict the network performance is through simulations such as using NF3. NF3 takes as input the network topologies, configurations, and the workload, and can simulate detailed packet level information, such as the packet loss ratio, flow jitter, and even specific buffer occupancies. However, NF3 is really slow. In our experiment, simulating 10 million flows on a 6,000 host topology took around 10 hours to simulate just 5 seconds. Fast network simulation at scale has been actively studied, particularly as data center networks continue to grow in size and speed. Prior works can be categorized into two groups: high-fidelity simulations and approximative simulations. They use parallel computing or machine learning to accelerate network simulation. However, they are still packet-level simulators. By simulating each packet-level event, they remain slow for large-scale networks, especially as these networks become larger and faster and the number of the packets will explode. Do we always need packet-level simulations to predict network performance? In many use cases, network operators are not focused on specific packet-level details. Instead, they are interested in aggregated network statistics, such as the network tail latency and utilization. They may ask, how are these aggregated network statistics affected by evolving workloads or training parameters? This leads us to ask, can we elevate the abstraction level of network simulations to focus on aggregated statistics, making the simulation faster without compromising fidelity? At a high level, we can abstract the network simulation as a function. This end-to-end function takes the network topology, configurations, and workloads as inputs and outputs the aggregated network statistics. As a concrete example, we focus on network tail latency. In M3, we use flow completion time and FCT slowdown as our core performance metrics. The network tail latency is defined as FCT slowdown at its 99th percentile. Can we use supervised learning to learn this end-to-end function? By avoiding the modeling of packet-level events, this supervised machine learning model should run significantly faster. Unfortunately, using machine learning to model this function is challenging due to its complexity. There are two main challenges. First, it's hard to represent this complex function in a compact way. Second, generating the training data sets for the machine learning model is too slow. We introduce M3 for faster network simulation at scale. M3 takes as input the network topology, configurations, and workloads, and outputs the network tail latency quickly. While M3 uses machine learning, it is designed to require only simple training examples. Thanks to its two key ideas, the trained machine learning models generalize to unthin workloads, topologies, and network configurations. In our experiments, compared to NF3, the packet-level simulator used as the ground truth, M3 achieves a 1,200 times speedup with only 10% estimation error in a 6,000 host topology. It reduces the simulation running time from around 10 hours to less than 1 minute. Let me start with M3's first idea, the path decomposition. Given a large-scale network simulation, M3's first step is to decompose the network-wide simulation into independent path-level simulations. For each path-level simulation, we can focus on flows traversing that specific path and estimate their performance in parallel. To start, we can prune the network topology at first. M3 has its assumption to further prune the flows for this path-level simulation. That is, flows that do not intersect this path have the second-order effect on the behavior of flows entirely along this path. Based on this assumption, M3 prunes flows that do not intersect this target path. As a result, M3's path-level simulation includes only flows that directly intersect the target path. M3 further categorizes these flows into two groups: foreground flows that follow the entire path, and the background flows that intersect only certain links along this path, but not all of them. The goal of M3's path-level simulation is to estimate the FCT distribution of the foreground flows along this path. Using path-level simulations as the building blocks for M3, M3 decomposes the full network topology into independent path-level simulations and then aggregates their performance to estimate the network-wide FCT distribution. The path decomposition helps M3 speed up the network simulation, but what about its fidelity? To verify this, we conducted experiments with 3 scenarios on a 256-host topology using NF3 as ground truth. For each scenario, we randomly selected 500 paths. For each path, we ran the NF3 path simulation where we pruned flows that do not intersect that path. Finally, we compared the tail latency between NF3 and NF3 path. We show the CDF of the magnitude of relative estimation error for the tail latency across 500 paths for each scenario. 80% of the paths have an estimation error of less than 10%. There are many unique paths for each scenario. Simulating just 500 paths and aggregating the results is sufficient to provide a good estimate of the network-wide tail latency with an error up to 6%. While the path-level simulation is quite accurate, it remains slow, with an overall speedup ranging from 3 to 14 times. M3's second idea is to estimate the path-level performance using machine learning to make it faster. This is non-trivial, as even a path-level simulation may have 10,000 foreground flows and 1 million background flows as its workload. Instead of feeding this complex path-level workloads directly to the machine learning model, M3 first uses a flow-level simulator to extract compact features for its machine learning models. So what is this flow-level simulator? We call it FlowSim. First, it's a max-min flow-level simulation. This means it operates without packets, and each flow sends at its max-min fail rate. Second, the simulator handles flow arrivals and departures as events. Third, because FlowSim operates on flows and not packets, it cannot tell you anything about the queue length at each switch. By ignoring those packet-level details, it's incredibly fast. It can complete a path-level simulation with 1 million flows in less than 1 second. FlowSim is fast, but not accurate. Given a path-level simulation, we compare the FCT slowdown estimated by NS3 and FlowSim across 4 flow size buckets. FlowSim tends to underestimate the flow completion time slowdown for small flows because the FCT slowdown of small flows is significantly affected by the queuing delay. Although FlowSim is not entirely accurate, it's efficient to extract compact features from workloads. To use FlowSim, M3 first runs FlowSim and then summarizes the per flow FCT slowdown estimated by FlowSim into a compact feature map. In the y-axis of this feature map, we first group flows into different flow size buckets. In the x-axis, we sample the FCT slowdown at specific percentiles and observe the discrete distribution of slowdowns for flows within each size bucket. These compact feature maps from FlowSim provide a concise summary of the workload and can distinguish between different workloads in a logical way. For example, when increasing the network load from 20% to 80%, we observe that FCT slowdown increases gradually, especially for large flows. When the workload is more bursty, the FCT slowdown also gradually increases, particularly for large flows. These results demonstrate that FlowSim can quickly summarize workloads into compact feature maps, and these feature maps effectively distinguish between different workloads in a logical way. For a given path level simulation, M3 inputs several feature maps extracted from the FlowSim for the foreground-background flows, along with other network configurations such as the buffer size, different CCAs, and their parameters into its machine learning model. Using NS3's FCT slowdown distribution as the ground truth, M3 corrects FlowSim and finally generates its own estimates for this path level simulation. For a path level simulation scenario, M3 effectively corrects the FCT slowdown distribution by FlowSim, making its estimates very close to those of NS3 for all 4 size buckets. Here, we show what M3 does and does not do. First, M3 assumes static routes known in advance. It does not handle dynamic routing strategies. Second, M3 predicts the distribution of FCT slowdown. It does not predict per flow or per packet performance. Lastly, M3 learns the impact of the network parameters from training examples. It cannot predict the performance of unseen protocols. How do we train M3? Based on M3's path decomposition, we only need to train it using 2-hop, 4-hop, and 6-hop parking lot topologies. Due to its FlowSim featureization, we only need to train M3 on synthetic workloads, such as the synthetic flow size distribution and different workload burstiness. For each scenario, we randomly choose network configurations such as the buffer size, initial window size, and different CC protocols. We train the models once and use it directly for different scenarios with production workloads and topologies. M3 generalizes to unseen workloads, topologies, and network configurations. We evaluate M3 using production workloads and the topologies. Given around 200 scenarios with different workloads and topologies, we use NS3 to provide the ground truth for network tail latency. We use Parsimon as the baseline, a fast packet level simulator for estimating network tail latency. Parsimon decomposes the full network simulation into independent link level simulations and then aggregates their results. In terms of the prediction accuracy, M3 reduces Parsimon's mean error from 18% to 10%. Besides, M3 is faster, achieving a 5.7 times speed up over Persimmon and being 3 orders of magnitude faster than NS3. We also compare M3, Persimmon, and NS3 on a 6,000 host Metas data center fabric. M3 is faster, more accurate, and robust, especially for different initial congestion control windows. M3 enables rapid design space exploration. We show an example of using M3 to explore the effect of initial window size on P99 FCT slowdown. Given a list of initial congestion control window sizes, M3 provides accurate predictions that are very close to those of NS3. Additionally, M3 runs much faster than NS3, reducing the mean runtime of each configuration from 8 hours to 25 seconds. To conclude, M3 is both accurate and fast for estimating flow level performance. It's 1,200 times faster than NS3 with less than a 10% estimation error for the network tail latency. This is achieved through 2K ideas, path decomposition and featureization via FlowSim simulation. If you are interested, please check our open source code on GitHub. The key takeaway for M3 is its general principle, which uses a reference system to extract features to model complex systems. In M3, we use the flow level simulator to extract a compact feature map from the complex workloads. Looking ahead, our future work includes learning from real networks data instead of NS3 and incorporating application level behaviors by using this general principle. Thanks.